Hello everyone. So in this part, we'll do a quick tour of Linux storage stack. Basically, we will see how Linux implements various file systems that it has and how users access various file systems that Linux provides. Okay. So a quick announcement. So Lab 5 options are out. So you can choose to do one of the two op- options for Lab 5. So details of it are on Brightspace and also on Piazza announcements. So why are we studying Linux storage stack? So Linux has exhaustive and modular storage stack, and it provides this amazing interface which makes it very easy to implement any file system that you can think of, and it provides an uniform interface for even for users, where users need not worry about the type of file system that they are accessing, and they can have a uniform access to all the files, okay, irrespective of the file system, underlying file system implementation. So Linux storage stack is modular and it's layered. Okay. And if we look at all the components, it's kind of relatively complex. Okay. Like your code or our data that goes from user space to actually the device, the data goes through various layers before it reaches magnetic disk, for instance. So there are various components of storage stack. So the main components that we'll look into in this part are like this syscall layer, and then under syscall there is VFS layer, which is virtual file system layer, and then comes the file systems. That's where any developer who wants to implement file system has to provide a module at the file system layer. And then there comes block scheduler, which is same for all the block devices, okay, which is the case with most of the disks or most of the storage devices. Under the blocks scheduler, we have device drivers, which actually hold the information about how to communicate with the device exactly. For instance, communicating with SSD is different from communicating with, for instance, magnetic disk. Okay? This part is abstracted by the device drivers. Okay? Note that file systems need not worry about uh, how to communicate with, for instance, SSD. Okay, so file systems are kind of independent from the actual device on which the file system stores. That means we can have, let's say, ext3 file system on SSD or on magnetic disk. And the developer of the file system need not worry about where the file system will be stored, like the actual device where the file system will be stored. This kind of makes file system implementation very modular and very nice piece of software, where file system only deals with mapping the data from the block device, or like from the blocks of the hardware or like actual device, to the inodes that VFS supports. That's it. Rest all Linux kernel takes care. Okay? And then at the bottom we have hardware devices, which are the actual devices that we plug into the system, or that are on the motherboard of the system, and device drivers communicate with the hardware. Another important piece of file systems is page cache. So page cache allows Linux to cache IO that happens through the to the disk or like to the block devices. So instead of directly writing to the device, page cache, as the name implies, it provides a caching interface for all the data that goes to block devices. So first, let's look at VFS. We know what syscalls are. We looked into in part two, where syscalls are interface exposed by the operating system to for various to expose various opportunities for the applications to interact with. So under the syscalls, we have virtual file system, VFS. So virtual file system is one of the largest components of Linux storage stack. So here, which is closely of 22,000 lines of code. And this provides this amazing interface of file, like everything in Linux, as I said in the previous, previous lecture, everything in Linux is a file. One of the main components that makes it possible is a virtual file system. Okay, even accessing network is a file. Like even network file system, again, it's a file. And this also provides like adding new file system to Linux relatively easy compared to different operating systems. Linux as of now supports close to 42 different file systems, okay, which is one of the highest file systems supported by any operating system. Now, what does VFS do for the applications? Like, what does VFS provides for when from the applications perspective? So VFS provides a common interface for the applications to access files, irrespective of the file system, irrespective of the underlying file system. Okay, and and file systems need not worry about interface to the users. Okay, and this makes file like accessing files in Linux so much easier, so much uniform, and no need to worry about underlying file system. And that way, even Linux itself provides most of its functionality as files. Like there is a proc file system. If you ever looked into proc file system, that's actually an interface exposed by Linux that allows us to see what are the contents of a process that is stored by Linux. So in short, VFS to applications provides a common interface through which users can access files irrespective of the file system. Okay. Similarly, VFS to file systems, it provides an exhaustive optimizations that they can use irrespective of the device or irrespective of the file system implementation. Okay. So for instance, page cache, path lookup, everything that is supported by Linux can be used by all the file systems because it is implemented in VFS. The only thing file system implementers have to do is to make is to remember the mapping from inodes to the blocks on to the block of the block device. That's it. Rest all Linux kernel will take care. Okay, and the file system implementers have to take care of defining functions to access certain inodes. Given an inode, they should know how to access certain file from the disk. And file system implementers, they just implement the file system, and these file systems could be added as Linux kernel modules, or they could be added as certain modules that you may need to enable when you are configuring Linux. So like if you have ever built Linux kernel, you need to do make config, that is where you can configure the Linux kernel to have different components. So there you can enable different file systems. If you write your own file system, you can add that as a module, and users can enable your file system by selecting that module during compilation. Okay, or your file system could be a dynamic module where users can install your file system while the kernel is running. So file system implementers, they just need to remember how to map inodes to the underlying blocks of the hardware of the device. Okay? They don't need to worry about how to communicate with the hardware. No, that's all taken care by Linux kernel. So in the next part, we will look at page cache and how page cache helps in making file access so much faster that we see almost constant access. We see almost as if we are accessing main memory when we are accessing files. Thank you.